In this video, we're going to look at some more examples using the fundamental theorem of calculus. Alright, so we can now find the antiderivative of a lot of different expressions. If it's just the power rule, we can do the reverse power rule, but now we can also undo the chain rule. This means we can now calculate the exact integral for all of these different expressions as well. Because once you have the antiderivative, you just plug in numbers to get your area under the curve. So this process has a lot of steps and can be a little bit daunting. So this video is here just so you can see more examples. Make sure that you're kind of keeping track of all the important stuff along the way. If your page is not organized, you want to kind of get better about working in columns and left to right and all that. And for this video, I'm just going to kind of go through all of them, but treat all of them as like a your turn problem. Pause the video, try it yourself first, and then compare it to what I did and see if you're on the right track. So here's the first one, the integral from 0 to 2 of x cubed minus 2x squared over x. So again, pause the video and just think about this one for a second. And this one looks really complicated. Again, we can't just straight do an antiderivative because we don't know how to undo a quotient, so we can't undo this division by doing just a normal antiderivative rule. Your second thought might be to make u equal to this complicated thing. But if you do that, then du is 3x squared minus 4x. And there's nothing for this to cancel out with. So actually, this is not a u substitution problem. So what the heck is left to try? All we can really do, use some algebra rules. We can split up this fraction into two separate fractions. This is kind of just like a trick. And then these simplify pretty nicely. And now this is just the power rule. So now we do the antiderivative using our power rule. And we're going to evaluate from 0 to 2. And just some small simplifying. Right. So now we plug in 2 first. It's always nice when they include 0 as one of the bounds because chances are like one whole section goes away. And we get negative 4/3 for our final answer. So this one is just a little simplifying trick. If you look at this one, you would probably instantly think of u substitution because the top looks pretty complicated. There's this little trick you can do whenever you just have a single term on the bottom. You can create 2 fractions instead of 1. And those fractions simplify pretty nicely. So that one's a little bit of a trick question in the sense that you might not have known how to do it yet, but now you know this little trick. This one's a little bit more complicated. If you look at this one, we have something whose derivative is also in the expression. So just a clear sign, we're going to use u substitution. And our u is the thing inside of something else. So our u is x cubed minus 2x. Take the derivative, du is 3x squared minus 2 dx. Divide that over, so we can plug it in. So now we get the expression. Actually, I'm going to have to explain something to you in a second. So we have 3x squared minus 2, cube root of u, and then du over 3x squared minus 2. And this one's one of the lucky ones because we kind of get this whole thing to cancel out, and our problem becomes the cube root of u du. You notice that when I rewrote this problem, I didn't write the 1 and the 2 because the 1 and the 2 have to do with the x values that I want. But when I rewrite it, now they should be about the u values. Well, what u values do I want to use? Well, what I can do is I can figure out the u values because u is related to x. Some extra work I have to do on the side. If x is 2, oops, it's a 2. Let me just erase that and rewrite it because that was very bad. X is 2, so that means I'm going to do 2 cubed minus 2 times 2. Which is 8 minus 4, which is 4. So if x is 2, u is 4, so now I can put a 4 up here. which means there's also going to be a 4 there. And then the other one is if u is 1. I get negative 1. So that means I can put a negative 1 here and a negative 1 there. All right, so this is called changing your bounds. All right, so I'm changing my bounds from to being about x to being about u. And this is going to be, let's see, this is u to the 1/3. I'm going to get u to the 4/3 over 4/3, evaluated from -1 to 4. All right. And since I changed my bounds to be about u, I don't actually have to go back and put it back in terms of x. I could rewrite this as, let's see, u was x cubed minus 2x to the 4/3 over 4/3, evaluated from 1 to 2, because those are the x bounds, but there's no reason to do that because I already have it in u in the numbers that I need, so I'm going to plug in 4. I'm going to subtract when I plug in -1. And for this problem, we'll just end there. Just some simplifying. 4 to the 4/3 does not turn out nicely because there's no nice cube root of 4. So we'll just leave it there. This is the basic idea I want you to get from this example, is that when you're doing an integral, you can change the numbers from being about x to being about u. And then you don't have to go back at the end. You just keep it in terms of x and plug in those new numbers that you need. All right, so this is one other new thing about how you can do integrals using substitution. And here's the last example we'll do in this video. I think we've learned all the tricks now of you can split up fractions, or you can just keep your integral in terms of u. But now this one, again, there's a division bar, so there's something we have to do. It's not just a single term on the bottom, so we're not going to split up into multiple fractions. So really, the only other option is to make u equal to something. In this case, we're going to make it equal to the bottom. All right, then we're going to take the derivative. That is dx. I divide. Now I rewrite this expression. I just rewrote everything in terms of u, so I need to figure out what u is going to be. So if I plug in 1 into my expression, I'm going to get 2 minus 3 minus 2 is -3. All right, so that's going to be my new top bound. If I plug in -1 into my expression, I'm going to get -2 minus 3 is -5 plus 2 is +3. No, that's not right. Those are -3. All right, -3, -2 minus 3 is -5. Plus 2 is -3. Yeah, seems like it's right. And then these are going to cancel out. So my expression comes integral from -3 to -3 of 1 over u du. We haven't learned how to do this one yet. 1 over u is the one thing we don't know how to take the antiderivative of, but we're going from -3 to -3. If we're going from -3 to -3, there's no area, there's no width, so the final answer is 0. So I guess I lied about there being all the tricks. And this one, the trick is if the bounds are the same, you always get 0. So here are some important lessons. All right, always take the antiderivative when evaluating an integral. All right, make sure you're using the fundamental theorem of calculus correctly, or take the antiderivative and then plug in stuff. I've said this a bunch when we're doing antiderivatives and integrals. Plug in the top bound first. There are ways you can use the original function, but it's just, I think, more work. All right, so you can use the new bounds of your u values for your substitution, and that'll make the process a little bit easier.